Hello and welcome to the next episode. In this one, we are going to take a look how we can implement a stickiness effect to our fluid simulation. In our simulation class, scroll a little bit down. We will change our scene a little bit. Here I want to add another circle. So let's call this circle 2. Circle 2 is equal to a new circle. I always forget turning this one off. All right, so new circle, add. And I want this at the center position. This is canvas.width divided by 2. And a height of 400 at a height. And then I think we didn't allow like things like line width and color, and I'm gonna add this to the shape class now too. So I think no, this is the radius, but a color. I want to change the color. There you go, the color. And here in the circle, no, right. And here in the circle, you're already setting the color. Oh, actually, I don't need to do that. All right. So, well, let's do this anyways. Super. No, this should be fine. Okay. Yeah, this circle should have a radius of 75 and also in orange color. Oh yeah. Okay, I was a little bit confused here, but it's fine. And the other circle, I want to change the center to. Here I'm just going to copy this one and change the Y position to 200. And I think, yeah, we're going to change the polygon too, but later in this episode. So let's push the other circle. Circle 2. There we go. Just to make sure that everything's fine. All right. If you go back to the browser, you'll see that our two circles are now upon each other. Well, the second circle is below the other circle. And this is our little test scene where we're going to test the stickiness. And for the stickiness, I need to create another method. Now we're going to implement that formula you see in the paper. And I'm going to call this, I think I'm going to put this above handle one-way coupling, and I'm going to call this handle stickiness. Stickiness. Here I need to pass the delta time 2. And again, I'm going to iterate through all of the particles. And I'm going to iterate through all of the shapes. And as I mentioned in the last episode, please do a, well, you can, or it's a good advice to do a optimized way where you have a spatial partitioning or a partitioning algorithm of some sort, that you're not jetting every particle against every shape. But I'm going to do it anyways, just to show you how you can implement the stickiness algorithm. All right, and then what we're going to do in this for loop then is we will try to get the best edge of a shape, and we're gonna, well, if a particle is in front of an edge in a specific range, then we get the vector from the edge to the particle. and this direction vector will have the length or the distance between the particle and the edge, and well, and the direction. And with that data, we can calculate a sticky force and, or let's say displacement, because I'm gonna add this to the position, and yeah, then we can calculate this, and then we have some sort of a stickiness effect. All right. But first we need to create that method. So let's create that in the shape method and shape class. And I'm gonna call this get nearest vector. And here I'm gonna pass the position. I think, yeah, I'm gonna call this position. And then a maximum sticky distance, which will be, in which distance there is a position displacement applied. Okay, if the particle is more far away than the distance, then there will be no displacement applied. And if it's in that range, then there will be a displacement. So I'm going to call this effect distance. And this is our method. And here I'm going to return a 0 vector for now. Okay. Back to the simulation. Let's first implement the formula. First, let's retrieve our nearest vector. This is the shapes. Get nearest vector. I'm just going to copy this one. Here I pass the particle position and a constant, which we need to define first. So let's define that constant right below the plasticity parameters. I'm going to call this sticky parameters. And here I'm going to add constant max sticky distance. And I'm going to set this to the interaction radius. You can set this, of course, to a lower value if you want to. And then we have the constant k stick. There you go. Okay, and this constant k stick will be used in the formula. So let's go back to handle stickiness. Yeah, and here I need to pass the max sticky distance. Okay, then I need to check if the nearest vector, if we actually have a vector, because if it's null, there will be no affected particle. That means the particle is basically out of range for the shape to be, or to has a sticky effect. And then we need to check if the nearest vector with the length 2 is greater than 0. So if it's 0, then we will have some problems when we use the length method, because division by not division, but well, I think actually, one moment. Yeah, actually we can use it's greater or equal to than 0, because if it's not 0, if the length is negative, then we have a problem, because we are taking then the square root of -1, and that's not possible. Then we get an error. Okay, then we need to get the distance from the particle. That means how far away is the particle from the edge of the shape. And then we can implement this formula, or let's say a term of the formula, where we don't need to calculate a vector, or we are multiplying the sticky term with a vector then. And this is the delta time times this k stick constant times the distance times 1 minus distance divided by this dot max sticky distance, and this then by minus 1, and this is the sticky term. Then we can normalize this vector we got out of that method, and then we can create our displacement vector, and this is just the normalized vector scaled by the sticky term. Okay, and then we just have to add this displacement to the position. All right, and that's our handle sticky method. Handle stickiness method. Cool. And now we can implement the get nearest vector for our circle first, because that's the easiest one to do. Yeah, let's implement this one first. I'm just going to copy the shape method, because we're going to override it in the circle in the circle class. And here we first create a direction from the center position to the particle position. So we have to subtract the position with this dot position. This position here is the particle position, and this dot position is our position from the circle center. And then we have to check if the direction length, okay, is smaller than this dot radius. If it's smaller, then we have a collision with the circle. But we don't want to check for collision. We want to check if the particle is inside the effective it's inside the effect distance. Okay, and with this we just need to add the effect distance to the radius, and then we have everything. Check if a particle is affected by the stickiness. Then we can get, we can get the length right here, because we need the length in the if too. And I'm gonna replace this length right there. Okay. Then I can normalize the direction, and I can scale the vector. Here I'm scanning the direction vector, that the vector has now a magnitude from the particle to the edge of the circle. And this is done by adding the radius with the effect distance and minus the length of the direction vector. I would recommend, if you have trouble to understand what's going on there, take a piece of paper and try to paint this scenario on it, and then you will see that the magnitude of this vector will be well, this formula here. It's gonna make sense. And yeah, and if it's not in our effect distance, we will return null. And this is everything for the get news vector for the circle. For the shape case, it's unfortunately it's a little bit more complex. Actually, it's more complex than the get direction out vector and the isPoint inside method. But we are going to implement this after we checked if our circle is now working. And I think we should be able to check this right now. So I want to change the particle emitter position to where do I have that? There we go. All right. And the particle emitter position will be also at the center. So I remove the 400 here. I want to have this at the really top. And the direction should be 0 and 1. So it's pointing directly downwards. And the amount, I want to set this one to 5 and the speed also to 5. All right, and then I need to add this line here again because I just commented. And I think then we have everything to try that out. Okay. Okay, actually we don't have everything. I forgot to call this method, as I always do. And I'm gonna put this below the double density relaxation. And I'm just saying here, handle stickiness and pass in the delta time. And then I think I'm just gonna take a look if everything's working and I'll be back in a second. Okay, so yeah, I found some little errors. We actually have to change this one from this one to a greater sign. And then I made a small mistake in the circle. And here we need to change or remove this effect, the distance. And when we remove that and saved, refresh, and when go back to the browser, then we will see that we actually have a sticky effect. And if I add the stick constant, if I increase that value, and I'm going to refresh here, you can see that the stickiness is even greater than. And if I set this to 0, then of course you will see that there is no stickiness applied. Okay. And now we can implement the same thing for our polygon. This will be a little bit more challenging. Okay, so let's go back. In the shape class, we are, there's our method. We have to go through some things. First, we have to get a best normal position. Like, that means we have to get the edge, the nearest edge where our particle is located. And we can do that by, like we did in the get direction out method. And in the direction out method, we have to do a similar thing. Here we are also searching for a best normal. And in the net nearest vector, we also need to search for it. Instead, we are using a really small number. We are using a really high number. So let's add this one, these lines. And now I need to iterate through every normal first. So that means I'm just going to copy this for loop here. And instead of this vertices, I'm going to take this dot normals. Then I'm going to retrieve the vertex and the current normal. And also I need to get the next vertex. So that's not our current vertex, but the vertex for the next index. Okay, so this would be I+1. I'm going to call this next vertex. And this should be this dot vertices I+1. But we will run into problems when we do that like that, because if our index is, for example, we have 10 normals and our index is already at the end. That means if the index is 9, then we add 1 to that, then we have an index of 10, but we only have the normals and there will be no index of 10. Okay, so we get some sort of a out of bounds exception. And we can avoid this by a circular index. And we can do it like this, that we will, we will avoid this by using this method here. What this is doing, for example, when we have 10 normals again, this will be 10, all right? Then we have a modulo, and then we have vertices length. So we have 10 vertices, for example, or let's say 10 normals. 10 normals. So this will be 10, all right? 10 divided by 10. Okay, this will be 0. And the rest of this calculation will be 0. So this whole thing here will be 0, and this will be our next index. If you, just for example, if you take a number, for example 15, and take the modulo with a 10, then 15 divided by 10 is 1.5, and the rest of this, actually the division by 10, if you divide 15 by 10, you get just 1, because the 10s, the 10 can only be once in the 15, all right? But there's a rest of 5, so you will get a 5 back from the modulo. And here we're going to use this simple trick to make some sort of a circular index. Okay. All right. And now that we have this information, we can calculate our edge. We need to have a direction vector from one vertex to the next vertex. And this is just a subtraction again from the next vertex with the current vertex. Then we have to get the length of that edge, and this is just edge.length. Then we can normalize this direction from one vertex to another vertex. And then we are creating another direction vector, which will be a direction vector from our particle position. Actually from the vertex position to the particle position. And yeah. From the vertex position to the particle position, right? Yeah, and I have to add here a sub. Right, okay. One moment. Yeah, I think I called this variable wrong. This must be vertex to particle. There we go. And then we can calculate where our particle if we project our particle onto the edge, then we can calculate well, we get where the particle is located at this edge position. You can imagine this like you're having a sun in front of an object, and it's projecting a shadow onto a wall, and we can now get a number which says where our particle is located at the edge. And we can do that by saying, I'm just going to call this between vertices dot, and this is the vertex to particle dot edge. Now we know where our particles is located between the vertices, and now I can say if this dot product is greater than 0, so it's somewhere in front, or yeah, somewhere in front of the current vertex, and if the value or the particle is smaller than the edge length, that means that the particle is now between the two vertices which make up the edge. Okay, that means this if statement here. And if that's the case, we then need to calculate how much the particle is away from the edge. Okay, till now we just calculated where is our particle. Is it between, at which edge is our particle located? Okay, now we found our edge, and now we have to calculate how far away the particle is from the edge. And we can do that again with some dot products, and I'm going to call this one distance from edge, and this is again the vertex to particle with the dot product or with the normal. And with this value now we can check if the distance from the edge is smaller than the smallest distance, and if the distance from the edge is greater than 0, this means that the particle is actually in front of the edge and not inside. That means the particle is in front of the shape and not inside of the shape. And then we have to check if the distance is smaller than the effect distance, and this means the particle is in fact in the range of the affection for the sticky effect. And here we need this statement here. We need that to get the best edge, the edge where the particle is located. And if these all things are the case, then we can say the smallest is now the distance from the edge, and the best normal is now the normal, well, like the copy of the normal. And this is our whole statement, and at the end we have to check if there is a best normal, because we set it to null first. And if there's a normal, if there's a best normal, we can return the normal, but scaled by the smallest distance. If it's not, then we can return null. Okay, and this is our statement for, or our method for an arbitrary polygon shape, so a convex shape, not a concave one. All right. Back to the simulation. I want to just add or change the position of our rectangle. The polygon vertices will have the coordinates 600, 600, 850, 850, 600, 450, 660, and 630, and 420. There we go. And these are now our new vertices for the polygon. So let's save and refresh the browser. And I'm going to switch to the browser now. And here we can see our current simulation. I think I have to change the case stick. Yeah, I changed this one to 0.1 now. I'm going to refresh that one. And let's see if it's working. Now the particles should in fact stick to our small rectangle. You can even see that they get attracted to the rectangle, so I guess the value is still a little bit too high. A kind of interesting thing happens when you place the circle like this, and then you take the other circle and place it also like this. And you can see our fluid is taking a little turn. Pretty cool. And yeah, this is everything for this episode. This one was also kind of long. But yeah, I promise the next episodes, well, actually there will be just one, I think, no, two, will not take that long, hopefully. All right, then, see you in the next one. Hope you have a nice day and see you then. Bye-bye.